All right. Good morning, guys. I sincerely apologize that I unfortunately will have to be out again today. Um, but luckily, there's a lot of good problems that we can do in our textbook as we go into our next section. So our plan in this video will be to wrap up section 223, which was over finding average rate of change. So this is the same thing we would have done if I was in person in class today. So we're going to do this problem-based task for section 223 to start. I'll put the answers to the homework up here in the video for you guys to pause your screen after this and kind of look through. And then we have the beginning of our next section, which will be word problems where we have to build a quadratic function. Okay, so we're on page 59 in our textbook. It was right before where our homework was. So it says it is Super Bowl season. Teams have made the playoffs, have specialists evaluating every aspect of their field game. One team received news that their recently injured kicker's field goal kick is modeled by this function. H of t is the height of the ball in feet, t seconds after being kicked. If the football needs to clear a 17-foot goal post, will the ball make it over if this particular team member kicks it? And then what is the average rate of change of the football's height from the moment it reaches its max height to the moment it hits the ground? So good review of some work with quadratic functions too in here, where we're going to have to find some different key features of it. Let's rewrite our function. It's h of t equals negative 16 times x minus 1 squared plus 16. Let's start by just getting kind of a clear image of what this would look like. So this is vertex form, right? Vertex form being y equals a times x minus h squared plus k. So if this is in vertex form, we can identify our vertex. Remember, that's h comma k. So our vertex is going to be at the point 1 comma 16. Great. Let's find our y-intercept. We have h of 0 equals negative 16 times 0 minus 1 squared plus 16. So that's negative 16 times negative 1 squared plus 16. So we'd have negative 16 plus 16, so it'd be 0. So our y-intercept is going to be at the point 0 comma 0. Cool. So at this point, we can make ourselves a sketch of what this would look like. So we have our point at 0 comma 0. Then we have our point at 1 up 16. This is just a rough sketch. 1 comma 16. And even without touching a graphing calculator here, we could really think of this as our axis of symmetry right here, meaning we could mirror over a point, right? We're 1 unit away this way, we go 1 unit this way, we'd get to where it touches the ground again. That would be at 2 comma 0. So without doing anything with a graphing calculator, we were able to get what this parabola would look like. And now we can start answering some questions. So first, the question was, the football needs to clear a 17-foot goal post. Will it make it over? Well, it would need to reach a height of 17 feet, at least at its max. And it looks like our vertex only reaches 16 feet high. So we could say, no, would not clear 17 feet. And then it said, what is the average rate of change of the football's height from the moment it reaches its max height to the moment it hits the ground? Well, that would be from the vertex of 1 comma 16 to when it hits the ground at 2 comma 0. So it's really saying find the rate of change between these 2 points. Okay, so these are x's and y's. And remember, rate of change, we could think of it as y2 minus y1 over x2 minus x1. Okay, right? Subtracting our y's on top, subtracting our x's on bottom. We also wrote this yesterday as f of b minus f of a over b minus a, right? Different ways of writing it, just communicating subtract our y's on top, subtract our x's on bottom. So let's find our rate of change. So we could say, for example, 0 minus 16 on top over 2 minus 1 on bottom, negative 16 over 1, or negative 16. And then it wouldn't be the worst thing to communicate what this means in the units of the problem. Okay, that's a good skill for us to master. We did this last year a lot. So h of t was the height of the ball in feet, t seconds after it was kicked. Okay, so we think about what this negative 16 means. Well, negative 16 means it'd be going down or decreasing on average 16 feet per second. We're decreasing on average 16 feet per second. Okay. So that wraps up section 223. I thought that was a good kind of warm up for today. I'll put the answers to the homework up here for a second if you want to pause your screen and look through. These are just snipped out of the back of the textbook. I know it's kind of tough to read. If you want to pause your screen, these are the answers you should have gotten. All right. Next, we're going to do a couple examples from our next section. So our next section is section 231. So that's going to be building quadratic functions from a real-world context problem. So we're going to focus on problems like example 2 and example 3 today. So we're going to flip ahead to page 70. Okay, so it says an amusement park has commissioned the design of a steel roller coaster with a drop section that is modeled by a parabola. Part of the roller coaster's track will go through an underground tunnel. In this section, the roller coaster will dip 12 feet below ground level. The roller coaster will dip below ground level at a horizontal distance of 24 feet from the peak just before the drop, and then reemerge at the ground level at a horizontal distance 36 feet from the peak just before the drop. Okay. Find an equation of the parabola that describes the drop in the roller coaster's height from the peak. Okay. So let's process through this again. So let's kind of highlight the key parts of this. So it's going through an underground tunnel. In this section, the roller coaster will dip 12 feet below ground level. So that's important. Then the roller coaster will dip below ground level at a horizontal distance 24 feet from the peak just before the drop, and reemerge to ground level at a horizontal distance 36 from the peak before the drop. Okay. So we'll go from here. Okay, so first things first, they gave us a lot of information. So I would make a quick sketch of what we really have here, the given information. Okay, so the roller coaster will dip below ground level at a horizontal distance 24 feet from the peak before the drop. So out 24, we'll put this first point. Okay, and then it reemerges to ground level at horizontal distance 36 from the peak. Okay, so we're back to ground level 36 feet away. And then the roller coaster will dip 12 feet below ground level. So it's saying this lowest point here has a y value of negative 12, right? 12 feet below ground level. So now we need to write the equation of the parabola that describes the drop in height of the roller coaster at its peak. Okay, since we were given x-intercepts, we'd want to use intercepts form. Okay, so remember intercepts form, that's y equals a times x minus p times x minus q. then we really have the values of P and Q. Right? P would be 24 and Q would be 36. So really, if we're thinking about this function here, what we have so far is a times x minus 24 times x minus 36. So the only thing preventing us from having this written as just a normal quadratic function would be having the value of a. So that's what's new here, is that we have to be able to find a. Well, in order to get that, we need to have another ordered pair, another point that could help us figure this out. So we know our vertex had a lowest y value of negative 12. We could also find where the x value is using our x-intercepts. Remember, we could use p plus q over 2. It'd be 24 plus 36 over 2. So that would be at the point 30. So right here at 30, negative 12, that's the lowest point. Okay, and now we kind of have this image of what our parabola would look like. Right, it's coming down. This is a rough sketch. Let's redo that. Okay, so we're coming down from somewhere, going to a lowest point, and we're coming back up. Okay. All right, so now we have this point, 30 comma negative 12, that's acting as our vertex. So that can act as our x and y. So what we're going to do is, if we need to solve for a, knowing that this point is on this parabola, we can substitute in 30 in for x and substitute in negative 12 for y. That's going to allow us to solve. So y is negative 12. So negative 12 equals a times 30 minus 24 times 30 minus 36. So negative 12 equals a times 6 times negative 6. So negative 12 equals negative 36a. Divide by negative 36. So a would be, that would reduce down to 1/3. So now we could write out our original quadratic function up here, substituting in the a value that we know. So our function will be y equals 1/3 times x minus 24 times x minus 36. Okay, so that's example 2. I'll do one more like this. We'll look at example 3. So it says a suspension bridge has 2 cables secured at either end of the span by 2 supporting towers. The cables are attached to the tops of the towers. In the section between the towers, the cables form a parabolic curve. At their lowest point, the cables are 15 feet from the surface of the bridge. The towers are 400 feet apart. What is the vertical distance from the surface of the bridge to the top? And the vertical distance from the surface of the bridge to the top of the tower is 415 feet. Okay, so let's read that again. Vertical distance from the surface of the bridge to the top of the tower is 415 feet. Okay, what is the quadratic equation that describes this curve? Okay. All right, so we have this picture here. I gave us a hint. We need to place the origin right here at 0, 0, and then we can start figuring out the different parts of this. Okay, so the cables are attached to the top of the towers. In the section between the 2 towers, the cables form a parabola. So we see our parabola in here. Right here. At their lowest point, the cables are 15 feet from the surface of the bridge. So the lowest point right here, they gave us the y-intercept there. 0, comma 15. Okay, so that's our y-intercept. But also notice what that represents in the problem if this is a parabola. And the vertex are 0, comma 15. It says the towers are 400 feet apart. So it's saying all the way across from tower to tower, that section is 400. And the vertical distance from the surface of the bridge, okay, so the bridge would be all the way at the bottom here to the top of each tower is 415 feet. So what they're trying to do is help us with some more points. Actually, we have this point here, we have this point here. Well, if it's 400 feet all the way across, then just half of it in here, that would be 200 feet going this way. And same deal. Oops, let's get a different color. And then also 200 feet going this way. Okay. So it's saying the vertical distance from the surface of the bridge to the top of the tower is 415 feet up. So this point right here would be 200 to the right, 200, comma, 415 up. And then this point over here, well, that'd be 200 to the left, so negative 200, comma, 415. Well, this is actually enough information to write our equation. We have some work to do, but we can do this. Why? Well, we have our vertex. The vertex is 0, comma 15. So if we have our vertex, let's use vertex form. Y equals a times x minus h squared plus k. And our vertex is 0, comma 15. That's our h, comma k. So we'd really have y equals a times x minus 0 squared plus 15. Just like example 2, what we really need to do is find a. Well, having these ordered pairs, these points is what allows us to do this. So now we could take one of the points, it doesn't matter which one, and we could substitute in our x and y. And that's going to help us solve for a. So we could put in for y, 415 equals a times, well, x minus 0 is just x. So really we'd have 200 squared plus 15. Notice this is an equation we can solve now. So 415 equals a times, we need to do 200 squared, 200 squared. So that'd be 40,000 plus 15. Let's minus over the 15 and come over here for our work. So 400 equals 40,000 a divided by 40,000. Calculator could help here. 400 divided by 40,000, your 0.01. Y equals 0.01, we're putting that in for a, times x minus 0 squared plus 15. That'll be our quadratic equation. All right, guys. I know this is tough. We're going to spend 3 whole days on this section, really, when we break it down. So don't stress out too crazy if you feel like that was a lot. 'Cause it is. They're tough problems. Okay, so we're going to really spend the rest of the week doing problems like this. So again, this is just day 1. We'll get this cleared up in class these next couple days if things aren't making sense. Our homework. So we're on Tuesday. So in our textbook, flip ahead a couple pages. It's going to be page 73 to 74, numbers 2, 4, 5, 8, and 9. Okay, 2, 4, 5, 8, and 9. All right. All right. Uh,